And then he also obtained the academic habilitation. But how it's pronounced in French?
Which one? You said?
Habilitation.
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 Yeah, habilitation.
Habilitation in 1991. And then he worked with FNRS as a research director in 1995. In 2002, he then switched to the academic path, and then he went to the university. He became a full professor at the University of Liège in 2007, and he served as a visiting professor in various institutes and universities across the world. For example, in Poland, Adam Macquarie University, and he is also currently the Vajra adjunct faculty at ARIES Nainital. So he's here with us. He also loved to teach, and he also provided training across the world in various countries like Chile, Poland, Qatar also, and some other countries also. So he is actively involved in 4-meter liquid mirror telescope, as we all know. So he has been coming several times here since 2012. Regularly, he's visiting ARIES and working with ILMT with his wife Anna. So we'll hear some of the adventure of ILMT and his adventure with ILMT. So John, welcome.
And, thank you very much for your introduction. Yeah, thank you very much. I apologize. I was convinced that he was at 3:30 and seminar at 4. Yeah, this was in my mind. Yeah, but as you said, well, it was clearly written in the mails that he was at 3:15. But usually I don't read about tea. Yeah, and so I thought 3:30 was a tea time. Yeah, but okay. Welcome to everyone. Yeah, and so I would just like my talk is principally addressed to the students of the first year, which I think are very rare here, very few, yeah. Because no, a few, yeah. Can you hand your raise your hands, yeah. So I find you, yeah. So it's not a majority, but
because their is over. So
yes, it's what I was told, yeah. And I would like to convince you that nature has invented everything before astronomers. Yeah. So, I'm not sure on which one I should press. Is it the white one? Yeah.
In the center.
Oh, in the center. So it doesn't work. Yeah. Yeah. Okay, now it works, yeah. So here I've just listed, the names of those participants who are presently active, but there have been many more before because our project has lasted for a very long time. Building a telescope and raising the funds from a single university is not obvious at all, yeah. But we were convinced that it should be feasible, and we tried our best, and it took about 20 years, to reach that level. So, among, the leaders of the group here at ARIES, that Mishra Kunstal, is leading the group, and then also from Canada, Paul Hickson, and myself from Belgium, Now, what I would like to share with you, is a very nice time lapse, that has been prepared by Himanshu Rawat, who is one of our technicians in Devasthal, and it is so nice. If you could switch off the light, Yes, all the lights, Otherwise, we won't see anything. And I draw your attention on the time lapse on the pollution of the sky by space debris, and satellites. You will see it's very, very, very visible. Can you still switch off the lights there? Yes, all lights, Yeah, astronomers don't like lights. They only like the stars. And of course, you will see the comet as well. You will see very conspicuously the Milky Way. And then, unfortunately, light being made by human beings on the Devasthal side, which we should avoid. Okay, so here is a video. So I just click on it, yeah. And well, just look at the passing, space debris satellites. You may see many of them, yeah, and the comet on the right side, yeah, which is just setting down. So well, the video is being made with a small camera, yeah, so it shows you the dangerous potential, yeah, of the space satellites, yeah, when you work with a big telescope, yeah, large aperture, which would be typically true for the LSST, yeah. But then you see also all the lights, yeah, on campus, yeah, and well, we should definitely avoid, yeah, having those lights in the future, yeah. And so I'm a little bit scared because I heard about the possibility of having more habitations, yeah, on top of the mountain, yeah, and well, it could be serious concern, I think, for the observations, yeah. Here is just a brief layout of my talk, yeah, so I shall address story of liquid mirror telescope, then speak to you about the camera obscura, formation of solar disk, yeah, then we'll also introduce the concept of convolution, yeah. Then, well, you'll see from camera obscura, we'll come to the basic principles of a telescope, yeah. Now, I will say a few words about Earth's rotation and the sun, and I forgot to take an umbrella here because, well, it was part of the demonstration, but we'll make it without. Now, about conic trajectories, and all that is related to liquid mirror telescope, as you will see in a moment. Then our special mode of observation with the CCD camera, because it's not a direct imaging, straight imaging, yeah, it's imaging in the so-called time delay integration mode. Well, then we'll come to the ILMT itself, yeah, where I will show you, yeah, its various components. Then what kind of science can you achieve with the ILMT? Conclusions and a general discussion. Yeah. So I come back one before. No. Yeah, I like to show this slide, yeah, because well, it shows you, yeah, view of the sun. And you see at the top on the right corner, yeah, there is a little blue, yeah, circle, yeah, disk, yeah, it's the Earth, yeah. And it shows the proportion of the Earth, yeah, to the only star, yeah. So that we should feel always, yeah, much humility and modesty, yeah, as beings, human beings, yeah, and try really to keep on Earth peace, yeah, yeah, which is in danger at the moment, as you certainly know. So the story starts in the 17th century. Already Newton knew that if you set a liquid, yeah, in a recipient in rotation around its vertical axis, yeah, well, it takes a parabolic shape, yeah. And it was Ernesto Capocci, director of the Naples Observatory in 1851, with the idea, yeah, to put mercury into the recipient, yeah, and use it as a reflective layer, yeah, to focus light rays, yeah. Attempt has been made, yeah, to construct a prototype in laboratory. Already 1875, yeah. He was an astronomer from New Zealand, and well, it showed the principle in laboratory, but never took it outside, yeah, under the sky. Well, Robert Wood, who worked as, well, it was not Space Telescope Science Institute, but at the university in Baltimore, yeah, succeeded in constructing a alpha meter and make star observations in a direct mode, yeah. He could see the stars, yeah, but their images were very unstable, yeah, partly due to the transmission of vibrations on the Mercury surface, and partly due to the fact that the rotation of the dish was not constant enough. Then, well, 1982, well, Hermano Borra revived his interest in liquid mirror telescopes, yeah, and he had the first proposition to use a hair bearing, so to avoid transmission of vibrations. And then, well, the amount of mercury you should set in a cylindrical recipient, yeah, could be a huge volume, yeah. And he had in mind that to reduce the amount of mercury necessary, what you could do is just a spin casting first of your mirror using a resin, yeah. So you set a resin in a recipient, it takes a quasi-parabolic shape, and after you just coat it, yeah, with a very thin layer of mercury. So the idea came from him too, yeah. 1994, Borra and Polikson constructed a first prototype, 2.7 meter, but well, it was under very bad skies and they had no optical corrector, they had no good CCD camera at the time, yeah. Nevertheless, Polikson participated to the construction of the NODO. NODO is the NASA Orbital Debris Observatory, and it was dedicated to the direct observation of space debris while passing near the zenith, and not with a TDI CCD camera, but with a detector with a highly amplified electronics, to make a time lapse of the passing space debris. Well, nevertheless, in 2003, Paul constructed, just very near to his house, a 6-meter large zenith telescope, which was in operation during 13 years, but not for sky observations, but he used it as a LiDAR, So he was just illuminating the upper atmosphere, with a, let's say, a light which would excite sodium atoms, and get the reflection, of that signal to probe the structure of the sodium layers in the mesosphere. Okay, so I come back one back, Well, here you see images. I don't know if the laser works. Is there a laser here? I don't see where it should come from, but there is no, but it's okay.
Point?
What? No,
Probably.
no, it doesn't matter. Doesn't matter, So you see, upper right, the 2.7 meter, UBC level mirror telescope, then the NODO on the right side, below a 3.7 meter lab liquid mirror telescope made by Hermano Bora, and then a view on the 6 meter, which is a very impressive telescope, in fact, but it was dismantled 13 years later, Now, our first contact with Hermano Bora dates back in 1996, when he asked us, well, would the liquid mirror telescope be of any use for observations of gravitational lenses? At that time, there were about 10 known over the whole sky, So the probability that you would get only one in your field of view, was 0. So I said no, And then in 1997, he came back to us saying, well, I'm organizing a conference in Marseille, Did you think over? And by that time, with one of my PhD students, we thought, well, the liquid mirror telescope, should unravel of the order of 10,000 quasars, So if there are 10,000 quasars, a significant fraction of those should be multiply lensed, And so, well, this would be prone for new discoveries, And this was our main motivation, and the project started in 1997, So you see, a long time ago. Okay, this is one of my favorite paintings, by Pierre-Auguste Renoir, 19th century. And well, at that time, so it's an impressionism painting. It was considered as a very bad painting because, well, you could see strange spot of lights, on the heads of some of the participants here, on their suits everywhere. And so, well, the guy, died very poor because no one wanted to buy his paintings. Today, the same painting, is estimated at a cost of $127 million US, So you see, you should always keep optimism. But now, well, these are pictures, mostly taken, in Pune. And you see that, well, on the floor, and on the wall, wow, you see things which look like, the light spots that we saw before. Well, different views, And this you may see every day around you, as long as there is some sun shining, Well, these were taken in Poland, on the, where you see vertical walls. And now I come, of course, to the camera obscura. So, a very nice camera obscura, is made of a poster tube, On which side, you set some, well, aluminum foil, with a very small hole, tiny hole, And on the other side, some butter paper, and you project, well, any source of light, and you look, over the butter paper what you see. And so, well, you know very well that if you look at a candle, well, the flame, will be seen at the bottom of the butter paper. and the bottom will be seen at the top. Yeah, so it's not strange. Now it's good to use such a pinhole camera while looking at the sun. Yeah. So as you may guess, what you will see on the butter paper on the other side, yeah, is a projection of the inverted image of the sun. Yeah. Now, the angle under which you see the sun, yeah, is easy to estimate. Yeah. Well, let's assume that my sun measures 1 centimeter wide. Yeah. And if I set it at a distance farther than 114 centimeter, I will not hide the sun. It should be a little bit closer than one. And when it is exactly 114 centimeter, I'm succeeding in hiding the sun. Yeah? Which means that its angular diameter is 1 over 114 radian. Yeah. Why? Because, well, the tangent of that angle is the opposite side divided, yeah, by the distance. Yeah. And since the angle is so small, 1 over 114 in tangent is about equal to the angle in tangent, in radian. Yeah, okay. So this is the angle. Now, let's assume that the length of the pinhole box is 114 centimeter. Yeah. Here is the first quiz. Yeah. What is the linear size of the projected solar disk on the butter paper? How much? So the first year students, yeah? Do you have any idea? How much could it be? So second year student, third year students. Bavia, how much? Yeah, 1 centimeter. Yeah, 1 centimeter, yeah? So 1 centimeter, because, well, when you divide 1 by 114, you also get, yeah? 1 over 114 radian, yeah? Okay. Now, as you know, yeah, in the foliage of the trees, yeah, there might be many holes, yeah, between the leaves. And so, well, what you should observe on the ground, yeah, are also images, yeah, of the solar disk. Now, of course, the angle under which, yeah, these solar disks are seen from the holes is also 1 divided by 114 radian, yeah, no difference. Now, second quiz. If you measure, yeah, the size, linear size of the solar disk on the ground, yeah, you find 5 centimeter, yeah. What is the distance between the solar disk and the hole in the tree? So first year student, how much? About, huh? Well, I know many of you know, yes, the answer. Well, you should multiply 5 by 114, yeah? And you find 5.7 meters. And this is a very nice way if you would like to estimate the height of a tree. Yeah? Just go under, measure the size, yeah, of the solar disk, and you get a good idea. Yeah. Well, actually, the largest size that my wife and I saw, yeah, were about 30 centimeters. Yeah. So it means that the trees were at a height of about 30 meters. Yeah. These were in the south of France. Yeah. Very impressive. So formation of solar disk in convolution, yeah, also we'll get there. So these are some more views, yeah, of the solar disk everywhere that you can see. Yeah, well, and the reason why I show the solar disk in my talk is that tomorrow when you will see, you will think about me, yeah, so I'd be very grateful, yeah. So you see solar disk. Well, this was the first to which we paid attention. It was in Haute-Provence Observatory in south of France. Well, we saw on the table this disk, yeah, and then we thought, whoa, what are these, yeah? Then we took a time lapse, yeah, and you see that, well, as there is a wind blowing, yeah, in the foliage, yeah, well, the holes are appearing, disappearing, and of course the solar disk are appearing and disappearing, yeah. And if you do the following, yeah, you would set the shadow of your head on one of the solar disks, yeah? So let's assume it is there. So, well, I look where I should go to project the shadow of my head there, and then I look, and then I would see the hole in the foliage, yeah? Well, it's a lot of fun. Yeah, so this is a, well, direct image here of one of those holes. Well, you see flashes of light suddenly, yeah, appearing and disappearing. Yeah, well, here, I just show you that just while playing with your fingers in front of the sun, you may project, yeah, similar solar disk, yeah. And if you measure the linear diameter of one such a disk, you will know the distance at which I was from the wall, yeah. Yeah, so, okay, now I come back to the camera obscura, and okay, I show the image, yeah, projected through the first pinhole. I assume that the candle is very, very far away from the box, okay? Now, well, if I look through the second hole, well, I see exactly, yeah, the same image, but translated, yeah, on the screen by exactly the separation between the two holes, yeah? So it's a, well, perfect translation because I assume that the candle is really located at infinity, yeah, on the left side, yeah? Here also, okay. Now, if I do the same with the heart, yeah, project the heart very far away from here. Well, I see that the resulting image is just, yeah, translation, yeah, by the precise separation between the holes, yeah. Now, if the holes are still closer, yeah, well, what I'll get a blurred image, yeah, of the three hearts. Okay, so in summary, when the holes are well separated, I have a well separated images. And as the separations get worse, yeah, the resulting image is blurred. Okay. I think now it's a quiz, yeah? Or not yet? Yeah, probably yes. So I assume that the source of light is the heart, yeah? Excuse me. Which is at infinity on the left side. That's the holes, yeah? Oh no, it's not yet the quiz. So I just show you the resulting image, yeah, of the heart if I set the screen, yeah, very near to the holes, a bit farther away, or still farther away. And what I notice is that the blur, yeah, is less, yeah, on the right than on the left, of course, yeah. But that the blur, so it's related to the distance, of course, yeah, where I project the images. And then it's also related, yeah, to where the number of small holes I consider, yeah. So to their size, in fact, yeah. So if H is a size, linear size, two-dimensional size is R square, of course, yeah. Okay, and what I find out finally is that the blur, yeah, is proportional, yeah, to the square of the size of the holes and divided by the square of the distance, yeah. Okay, good observation. Now, what about the surface brightness, yeah? Well, I know that if I consider the surface brightness, yeah, so same labeled, yeah. Well, larger will be the hole in size, yeah. Well, larger will be the surface brightness, yeah. So it's proportional to the square of H, yeah. But inversely proportional to the square of the distance because of geometrical dilution, yeah. So you see there is a compromise, yeah. If you would like to see a very nice image of the sun, well, with very clear details, yeah, you should be in a very dark environment, yeah, and at a very far away distance from the screen. On the contrary, if you would like to see a bright image of the sun, yeah, well, but slightly blurred, you should come very close to the screen, yeah. So now comes the quiz. So let's assume that the hole is the shape of the heart, yeah, represented here in blue. Now that the light, the source of light, yeah, is the sun, very distant from the hole. And now, if I set the screen here, yeah, should I see, well, yellow heart inverted or solar disk yellow inverted or non-inverted? Yeah, so only 4 possibilities. Yeah, who thinks that it should be a heart, yellow, inverted? Four persons like the heart. Yeah, who would think that it should be well, solar image, yellow, inverted. Who are for solar images? Yeah, there are several. Yeah, so in fact, it should be a yellow heart. Yeah, so good points here. Yeah. Now, second quiz. If I go very far away, yeah, set the screen here. Should it be a heart or a sun? Solar disk image. Who is for the sun? Yes, several. Who is for the heart? The heart. You don't like hearts? No, you're right. It should be inverted solar disk. Yeah. Okay. And now, well, I intend, yeah, well, during one of my next visits, yeah, to deliver a series of courses, yeah, on optics, yeah, well, image formation, well, interferometry, things like that. But then we would demonstrate, yeah, these simple relations that the distribution, yeah, of surface brightness on the image that you are looking at, yeah, is a convolution product, yeah, of the shape of the hole by the shape of the sun that you would see if the hole was infinitely small, yeah. But this would take 10 minutes, so I have no time today, but we will do that, yeah, in the future. Yeah. But it's a lot of fun. So what we did in Liège, yeah, well, we took, yeah, a piece of blackboard, yeah, and perforated to make different kinds of holes. As you see, some are star-like, some are square, some are, well, elliptical or spherical, yeah. And then it was oriented along the south direction where the sun was shining, yeah. And then with a sheet of paper, we were looking at the projected images, yeah. And what you see is that, okay, I come back, no, it goes the wrong direction. So here, when we are very near, well, we see clearly, yeah, the whole shapes, yeah, just like the first answer to the quiz, yeah, we were seeing the yellow heart, yeah. But as we go further away, well, we see some blurring starting, yeah. And when going still further away, what you can see, yeah, we can see a cloud, yeah, passing over the sun in the four upper images, yeah. And now I'm still further away, and then, well, you see perfectly through all the holes, yeah, the same image of the sun, yeah. Well, here is still magnification of those images, yeah. And the image where you have, well, the more details is the second one there because it corresponded to the smallest hole, yeah. But it is the faintest one too, of course, yeah. Well, and if the diameter of the pinhole, yeah, tends to 0, yeah, should we see an infinite, you know, resolution, angular resolution? Well, no. What we would see, of course, yeah, is a airy disk, yeah. So we would be limited by diffraction, yeah, of light, because when the size of the hole becomes comparable to the wavelengths of light, yeah, well, you have diffraction effects, yeah. But under an atmosphere, yeah, it's even worse, yeah. What we obtain, yeah, is a blurred image because of the turbulence, yeah. And so with the help of atmospheric scientists, yeah, we hope that we would be capable of solving, well, such issues. And it is the case, yeah, with using adaptive optics, yeah, you may find some repairs to that situation. Now, could you do the same, yeah, using reflection of light, yeah? Yes. So here what I show are just mirrors, yeah, over which, yeah, I glued, yeah, cardboard, yeah, perforated with different holes, yeah. And then, well, I use it to reflect the light of the sun, yeah, on the wall here. So you see, I'm holding here the mirror, so I'm very clear, very, very near, and I see perfectly, yeah, the shapes of all the holes. But this is magnification. Now, if I go further away, well, I'm getting blurred holes or blurred solar images. And if I still go much farther away, well, you see here the 5 images here of the solar disk here projected here. So I think this is a good experience, you know, when you're visiting schools, yeah, to get scientific interest. in what people can see every day. Okay, now back to the camera obscura. So we know that if we look at a candle far away from the first hole, we see an image inverted, yeah? And now, what astronomer would like to, yeah, is not to get, yeah, a second translated image of the candle, but to get the second image overlaid over the first one, yeah? So that you get, well, some amplification of the light. And so what you need to do to get that, yeah, well, just use a small prism and deflect the light ray, yeah? So you said, you see a little prism, it deflects the light ray, and wow, this is good. Now you want to do the same, yeah, through the bottom hole. So of course you invert, yeah, the orientation of the prism. You get another image overimposed, yeah. Then what you do in the center, well, just place a, well, prism, but with two faces which are parallel. And what you are constructing, in fact, is a converging lens. You agree? This is a converging lens, and this is what a telescope is made of, yeah? Just objective, yeah? And then what you would do to look at your image, you would use a magnifier, yeah? Which is known as being an eyepiece. And well, this is how a telescope, yeah, is made. Now, well, constructing big telescopes using glass lenses, yeah, is very expensive, and there is a limitation in size, yeah, above 1 meter. It becomes very critical because of all kinds of aberrations. So, well, the idea is why not to use a reflection, yeah. Now, if you use a flat mirror and look at the distant object, of course, light rays, yeah, will just go back to the distant object, and it's not what astronomers want. What we want is to concentrate these light rays, yeah, into a single point, yeah. Now, to do that, you have to curve your mirror, and well, during the lectures, yeah, I shall deliver one day here, yeah, we shall demonstrate that the reference surface, yeah, is in fact a paraboloid, yeah. So a paraboloid is what you need. Now, in the case of a liquid mirror telescope, yeah, as I said, we are setting liquid mercury in rotation around the vertical axis. And then you could demonstrate that the focal length, yeah, is proportional to the gravity, yeah, and to the inverse of the square of the angular velocity. So faster is the ball spinning around the vertical axis, shorter is the focal length. Yeah. And well, I just drop here. Well, this is an animation. I hope, yes, you see it works. So we are just now increasing, you see the angular velocity of the dish, and you see that the focal length shrinks, yeah. And well, the acceleration acting here on a small volume of mercury is just gravity and the centrifugal force, yeah, represented in blue. So you see, as it slowed down, well, centrifugal force disappear, and the light rays go back to infinity, yeah, rather than when it reaccelerates, yeah, well, the centrifugal force take over. Okay. Now, well, with our telescope, yeah, well, or with any telescope, you're limited by the diffraction, yeah. So the angular resolution you may achieve, yeah, depends, yeah, on, well, as we'll see, on the wavelength and on the diameter. Now, so looking at any star, yeah, with a small telescope, yeah, you would see ARIES, yeah. Irrelevant if the star is massive or not, is blue or red, is hot, is made of iron. So all stars would look the same, yeah. But the size of the central dot, yeah, would be proportional to the wavelengths and inversely proportional to the diameter of the dish. So if you take a larger dish, yeah, well, you gain, yeah, okay. Now, if you look at an extended object, well, with a small telescope, yeah, well, here we assume that you are looking at an exoplanet, yeah, you would see a blurred image. With a larger telescope, well, it would be better, yeah, but still. And this drives, yeah, the justification to construct, yeah, ever larger and larger telescopes, yeah. But as you know, over a certain size, probably around 50 meters, yeah, it becomes technologically very difficult, yeah, to construct larger mirrors. But what to do? Well, in fact, already you see, in the 19th century, Piso and Stefan, yeah, came with the idea of, well, considering two single telescopes separated by very long baselines, yeah, and try to, well, interact the light from the two telescopes in a coherent way, yeah, in a coherent way. And what they demonstrated already then is that the angular resolutions that you would achieve would be comparable to that of a single telescope having the same diameter, yeah? So you see, here you still observe, yeah, the airy disk due to the single apertures, but it's crossed by fringes. And those fringes, yeah, provide you the angular resolution needed, yeah, to resolve, I mean, very, very small objects, yeah. So with a small telescope, a blurred image, with a larger one, it's better. But if you could make use, yeah, of very long baselines, yeah, you could, of course, yeah, overcome that problem of angular resolution. And you know that many interferometers, yeah, exist already now and are in action, yeah. And so in the context of the lectures I would deliver, I would, of course, address, yeah, those aspects of image reconstruction. Now about Earth rotation and Sun and star rotation, yeah. Yeah, this is interesting because in the case of the liquid mirror telescope, yeah, we know that, well, the telescope is fixed, but the stars are passing over, yeah. And so, well, they will lead, well, they will show some trails in the focal plane, yeah. So how to record those images, yeah? And what are the trajectory followed by the stars in the focal plane? Well, to find out, yeah, it's very simple, yeah. Well, let's consider, for instance, first the sun, yeah. So the sun. Well, the sun during the day, what it does, yeah. Well, let's assume that the south-north axis, yeah, is along that direction. Well, the sun being here, well, just describe a circle, yeah, around the point of intersection, yeah, of the south-north axis with the celestial sphere, yeah. So the light rays that I see from the sun, yeah, will describe, in fact, a cone of light, yeah? So now, let's assume that I intersect with a sheet of paper, yeah, that cone of light. What I will see? Well, I will see a circle. But now, if my plane of reference is slightly inclined, yeah, well, I will intersect a cone with an inclined plane, which will be a conic trajectory, okay? And this is about conic trajectory. So you see, depending, yeah, on the orientation of the plane with which you cut the cones, you may see either, well, a circle, an ellipse, well, here a parabola, or a hyperbola. And in the case of the liquid mirror telescope, it's exactly the same, yeah? We have to consider the star, which declination is plus 29 degree, 20 arc minute, and wonder, well, what is a cone described by those stars around the south-north axis? And what is the intersection of that cone with the plane of our detector? And in our case, it is well, the trajectory of a hyperbola. So this shows you exactly, yeah, what happens here in Devasthal, yeah? We obtain such a trajectory. It looks like a hyperbola, but very near to the central area. So around here. So what we will need, first we will need to rectify that, yeah, hyperbola along a straight line, and then still record, I mean, the stellar images while they are moving. Oh, but before, yeah, another interesting demonstration. We just took time lapse of the shadow of a lampshade on the 21st of September. 21st of September, yeah, so it's not a long time ago. And you see the trajectory of the shadow of the shade on the ground, yeah. So it takes time. Well, it was lasting about 7 hours, I think, yeah. And there is a quiz, yeah? What is the trajectory followed by that shadow? Yeah. Knowing that it was made on the 21st of September. Yeah. And if you would have made that experiment here in Nainital on 21st of September, the answer would be the same. Same as in Belgium, same as anywhere else. Yeah. So does anyone have an idea of what the trajectory looks like? So what I show here are three locations of the shadow as a function of time. And you see, it's along a straight line. And the reason is the following, yeah? On 21st of September, the sun is in the equatorial plane. So the direction of the sun with respect to the north-south axis is a straight line, yeah? It's perpendicular to the south-north axis, yeah? And so it describes a degenerated cone of light, which is a plane. Now, a plane of light intersected by any other plane is always a straight line. And therefore, on 21st of September or 21st of March, wherever you are on Earth, yeah, you will always see linear trajectories. Yeah? So, okay, now, how to build at home your own liquid mirror telescopes? Well, what I show here is that this is just a piece of wood, yeah, on which will sit the mirror, of course. And where there are three holes and three boards, just to adjust the horizontality, yeah, of the sheet of wood, yeah, with respect to the ground. Then, well, we just bought a gramophone, old gramophone, yeah, for €1 because no one uses them anymore, yeah. Then we bought, well, it was a plate for cake, yeah, on which, yeah, we would just pour either some oil, yeah, or, well, honey, and then just put it on the gramophone, 33 turns per minute, yeah, and of course, yeah, well, the substance inside with a high viscosity, yeah, some oil, yeah, would take a parabolic shape, yeah. And so you see just above, yeah, we set a piece of butter paper, and we looked, yeah, at the image of a distant light, a lamp that was hanging on the ceiling, and well, you could very well see, very clear details, yeah, what is the power of the light, yeah, what is the number of amperes, etc., etc. So it's very easy to do. Now, well, okay. Now, in the case of the ILMT, of course, the lamp would not stay stable in the sky; it would move. So we would need, yeah, either to translate our detector, yeah, with the same velocity as the star, yeah, drifting in the focal plane, yeah. Or what we do, yeah, with modern CCD detectors, yeah, we are just drifting the charges, yeah, at the same speed as the star is passing in the focal plane, yeah. But before knowing that, you need to rectify the parabolic trajectory along a straight line, and for that you need an optical corrector, and I'll come to that point in a moment. Yeah. Well, typically at the end of the night, what you are obtaining, yeah, because we are constantly reading the CCD, yeah, is a very, very long movie, yeah, of the star which have passed in the focal plane. And so, well, the time of integration, yeah, in our case, is typically 1 or 2 seconds, yeah, so a little more than 1 minute. And well, we are reaching, yeah, well, magnitude 22, yeah, in all the spectral bands, so which is already nice. And if you would like to co-add, yeah, your data, for instance, after 6 nights, yeah, well, you would gain 1 magnitude, yeah, already. Oh yeah, now, well, in our project, I would like to mention that 2 persons, yeah, helped us a lot, yeah. They were the two chairs of the governing council, yeah. So one was Professor S.K. Joshi, and I was very glad to see that the Science Center, yeah, was named after him in Devasthal, yeah, very nice, yeah. And another governing council chair who helped us a lot, yeah, was Professor Govind Shwarup, yeah. Well, the two with whom we have worked very, very closely, yeah, during, well, each 5 years about, yeah. So very nice to remember them here. Now I come here to the 4-meter ILMT. And well, just tell you that it was a very inexpensive telescope compared to other telescopes. Yeah? Probably the ratio of the cost is a factor between 20 and 30. Yeah. For the mirror, even more, it would be a factor 50. Yeah, because well, grinding and polishing glass mirror, yeah, is much more expensive. Yeah. But you see, well, the main components, yeah, consist of the mirror, of course, yeah, sitting on a hair bearing, and which sits on a 3-point mount, yeah, and we're just adjusting, you know, well, as near as possible to the zenith, yeah, its axis of rotation. Then, well, you have the upper hand, which contains the optical corrector that I'll describe in a moment, well, CCD camera, and then alignment mechanism. Well, this was, I said, it's a long story, yeah. It started in 2007 that we received the first funds, yeah, to start building the structure. Now the mirror, yeah, is made of foam, yeah, to which we gave yeah, a spherical shape, yeah. And after it was sandwiched between sheets of sheets of carbon, yeah. And these were later, so well, here you see, yeah, you see after having sandwiched, yeah, the foam core, yeah, between carbon fibers, yeah. So this was at AMOS, yeah, in Liège, yeah. So they were just trying to find whether the telescope structure, yeah, made good sense, yeah. So a long time ago. And here I have an interesting video summarizing, yeah, how we spin cast, yeah, the mirror. So here we are just preparing, yeah, some polyurethane, yeah. So it's a kind of well, liquid, it's liquid, yeah, when you're pouring it, but after typically 30 minutes, it gets solid. So you should do that operation very fast, yeah. So therefore we were many in doing that operation, you see here. So the reference shape is spherical at the beginning. Now, while pouring the polyurethane, yeah, the shape would get quasi, yeah, ellipsoidal. After typically 20 minutes, yeah, well, the resin becomes solid. And after that, we can start, yeah, filling the mirror with mercury. Here we are. So these were our first tests, yeah, at AMOS. So we are pouring a quantity of about 50 liters of mercury inside. And after you have to spread it out, yeah. And this is done manually. Well, here you see a PhD student who was François Finet, who came here for 1 year, I think, as a postdoc. And it's just by giving, you know, phases of acceleration, of deceleration, yeah, that you succeed in spreading very well, accurately, yeah, the mercury, filling in the holes that you see sometimes appear. And when there is no more holes, then there is a motor inside the air bearing, yeah, which takes over with a constant angular rotation, precise to 1 part in 1 million, yeah. So it's a very, very accurate rotation. Okay. Now shipping of the ILMT started in December 2011. You see packing of the mirror at AMOS just before Christmas. So it arrived here in Devasthal you see, for spring 2012. And I remember it was problematic when passing through Boali, yeah, because, well, they had to dismount, I think, some telegraphic pillar. Arriving in Devasthal. So the mirror transported to the top. And then, well, civil engineering, construction of the ILMT dome started, yeah. So the dome is also very inexpensive, yeah, because, well, the dome is not rotating, yeah, and there is a simple hatch that you may open or close, yeah. But compared to the DOT dome, yeah, it's of course very much more simple and inexpensive. 2013, you see the early construction of the dome. Here's a metallic structure. And when we were present when this happened, and we were really worried to see those men working without any security on those structures. You may see on my face, yeah. The reason was that a few minutes later, yeah, they were just hanging 1 ton beam, yeah, on top of the structure, and suddenly, yeah, it fell down, yeah, and the structure started, yeah, to shake, and the people, well, fortunately, no one fell down, but it was extremely risky operation, yeah. So, I mean, these people are very courageous, really, yeah. So you see, as time goes, yeah, structure takes shape. Well, here are members of the PEDVAC team, yeah, who, well, who should be mentioned because they did a fantastic work, yeah. Now, even very impressive were the digging of holes, yeah, in the ground, yeah, to find good earth grounding, and these were 10 feet deep, yeah, and everything was made by hand, yeah. So impressive, yeah. And I remembered that statue, yeah, here very nearby, yeah. And we should really keep our admiration for all those people, yeah, working in very hard, harsh conditions, yeah, and well, being eclipsed after, yeah. Okay. Now you see that Amos came to erect the telescope only 2017, yeah. So it took 5 years to get the dome constructed, yeah. Okay, now construction is achieved. Inside and outside. Well, here you see the mercury tank, yeah, where 50 liters of mercury, yeah, are poured in, yeah. And then, well, just at the top, there is a box with charcoal, yeah. So what we are doing, yeah, to prevent, well, mercury vapor contamination in the dome, yeah. Well, you will see that the mirror will be covered later on with a mylar film, yeah. And at the center, we will be sucking the mercury vapor, which will be transported, yeah, to that rectangular box where we have the charcoal, and the vapors will get neutralized. And when we measured the vapor concentration all around, yeah, well, it was much under the limits of anything being dangerous, yeah. So if you take a lot of care, yeah, there is no danger in handling mercury, just like with nuclear material. If you take all the precautions, it's not dangerous. If you don't take all precautions, it can be extremely dangerous, yeah. So several images, yeah, of the ILMT. Probably most of you, yeah, have already seen it, yeah. Well, here we have a direct view on the air bearing, yeah, which is protected within a plexiglass box, yeah, to maintain a constant temperature inside. Now, well, you know, there are many power outages, yeah, in Devasthal. When there is one, after 5 minutes, yeah, well, generators are taking over. But in the meantime, what we need is not to stop, yeah, the rotation of the air bearing, and therefore there is a UPS, yeah, which has been well developed by Mukesh, yeah, and it's working extremely well. Now, to provide air compressed air, yeah, to the air bearing, we have 2 parallel air bearing air system. So we have 2 compressors that you see on the lower upper left, yeah. and two air tanks, so that if one fails, yeah, the second one take over and provides the compressed air. Then your air needs to be highly purified, yeah, no trace of water, no trace of dust particle, yeah, and therefore, yeah, the air, yeah, is filtered with a very complex system, yeah, that has been designed by Polikson. Now you see here on the top, yeah, the optical corrector, and it's made of 5 lenses, some of which are tilted and some of which are out of axis, yeah, to correct the hyperbolic trajectory along a straight line, yeah, which means that the corrector is asymmetric. And Amos always refused, yeah, to try installing this corrector because they said, well, how shall we know how to install it, yeah, its orientation, yeah. So we had to find out the solution. And the solution we found, yeah, was the following. We were just hanging, yeah, a wire, yeah, with a pendulum, yeah, and waiting for known local time. Then we knew that the shadow would be projected along the north-south direction. And it's what we were waiting for, to see that the shadow, yeah, was oriented north-south at local noon. And then very, very fast, yeah, Kushal would orient the corrector in proper direction. Yeah. Now, well, we have an interface between the camera and the corrector, which was designed in Belgium. And when it arrived in Devasthal, well, Himalayas was very much afflicted because it was all broken inside. During transportation, the roads, yeah, with a, you know, very cheap truck, yeah, there were a lot of shaking motions and it destroyed it completely. So we had to ship it back to Belgium, repair it, and bring it back, yeah. And then Hitesh accompanied, yeah, the driver, yeah, and in front of any hole would say, just drive very carefully, yeah. Then we have a CCD camera, which works in the time delay integration mode. So it's a 4K by 4K camera, which is being cooled down, yeah, to minus 110 degrees Celsius, just to reduce the background noise, of course. At the moment, we have 3 filters, the Sloan filters, GRI, and a dark slot, yeah. You see here the trail with the filters, yeah, just behind the CCD camera. Well, we have a folding platform, yeah, to get access to the prime focus. And before pouring mercury, what needs to be done is to clean the mirror, of course, yeah. Well, this is very carefully done, yeah, with isopropanol and then a special vacuum cleaner for mercury droplets, yeah, which could potentially be present. Then we need to cover, yeah, the mirror with mylar. The main reason is to prevent any friction between the air and the mercury that could induce the formation of ripples and will affect the image quality. At the same time, yeah, it helps confining the mercury vapors, yeah, inside before being transferred to the charcoal neutralizer. Yeah. So this is a top view, still a rather aerial top view of the ILMT. And here, the first time we tried to close the surface, we could not succeed. Yeah, Paul was here, and the reason was we were conscious that the quantity of mercury that had been delivered was too small. Yeah, so we lost probably 1.5 years to get the HEMOS respond to our request, and when they provided a few more liters, it worked. Yeah, so this was the reason. So first light finally happened, yeah, you see in spring 2022, so a little more than 2 years ago. So we were very, very happy, of course. Yeah. It was a nice evening. Well, here we control, yeah, the mercury vapor, yeah, inside the dome. And well, a critical value, yeah, if you are under 25, that you don't see here, you could still work without a mask during 8 hours a day. Yeah. So you see, we never reached that level of criticality. And of course, we have celebrated, yeah, first light, and then, well, more observation with the ILMT. Now we are We already ate ILMT number 7, but we forgot to eat ILMT number 6. So well, anyone interested, may join. Okay, aerial view of the Devasthal Observatory, which we find a marvelous place, really. Yeah, it's a really nice site. Yeah, as one may see here. So we have a really great pleasure. Well, we are among the astronomers who spend most time there during 10 years. Yeah, because most of the year we were spending there about 6 weeks minimum. Yeah, so 6 weeks times 10 is 60 weeks. So it's about 5 years of our life. It's nice, but we really love that place. Yeah, it's a really nice area. Okay. Well, sometimes we met very harsh conditions. Yeah. So we had to leave the observatory. Yeah, and then walk during 15 kilometers with luggages. Yeah. And then everybody was dead on the next day. Yeah. Nice place where, you may see birded vultures, yeah, coming with bones, yeah. And just in front of the window of the ILMT data room, yeah, there is a stony area, and they just drop the bones to break them, yeah. And so if they don't succeed the first time, they land, they take it again and let it go down. So during the day, we are enjoying this. Yeah? Now about science. Well, you see here, it's a night assistant speaking to a professional astronomer. Yeah, he says the universe isn't coming to an end. You just left the cap on. Yeah, so we are very happy to have competent night assistant with us. Yeah. Now this is the trajectory. Yeah, projected here on. Well, it's a galactic representation of the Milky Way. Yeah. And you see the trace of the Liquid Mirror Telescope field of view, yeah, during the full year. So we are passing very close to the North Galactic Pole right now, but also crossing twice, yeah, the equatorial plane. So, well, all our targets, yeah, are, of interest to all astronomers, because or you're extragalactic, or you're galactic, or your solar system, and you find interest in all of those, yeah. So here, an example of an open cluster, yeah, projected against Milky Way. Well, here, an example of a planetary nebula that you see as the green disk that you see here. Now, this is another one known planetary nebula, NGC 7321. You see, it appears in a very conspicuous way. Now we are detecting a lot of space debris and satellites. These are 5 consecutive detections on different nights, yeah, of a Russian satellite, which is not operational yet any longer. Yeah, but you see, we are using a green, blue, and red filter. Well, here you see passing space debris, probably in a fast rotation, yeah, around an axis. Yeah. Now here, during 7 consecutive nights, yeah, sometimes, yeah, we are detecting the same asteroid. So you see it through different filters, yeah, and then there is a passing space debris seen in blue. Well, sometimes very strange objects appear, but now you may play with the dynamics, and then you find out that this is just a interacting galaxy, yeah, double interacting galaxy, yeah, with a mass transfer from one to the other. The next slide still shows you here something similar. So 2 interacting galaxies, yeah. Now, well, our telescope, yeah, is very widely open, yeah, f2.3 about, yeah. So very sensitive to extended objects like low surface brightness nebulae. Here we see many reflection nebulae, but not only. This is still one reflection nebula. On the next slide, you will see emission line nebula, which emits a light, yeah, in H alpha mostly. Yeah. So you may see, well, a lot of details, yeah, in this nebulae. Well, of course, yeah, we are also detecting well, interesting objects like supernovae. So here is the first one that we monitored, yeah. And so then trying to construct light curves, yeah, of these objects. So in conclusions, yeah, well, the ILMT is an instrument, yeah, entirely dedicated to a photometric and astrometric variability survey, as well as to enter, yeah, well, astronomical transients, yeah. This is the main reason of being of a branch, yeah. And well, we are limited, yeah, by the local scene, yeah. We already had images, yeah, well, at the level 1.1 second of arc, yeah. Now, the plus is that we have continuous zenith observation. So if the night lasts 10 hours, and we are observing during 10 hours, recording ILMT data, where we obtain the best image quality because we are working at the zenith, yeah, where atmospheric extinction is the least, also light pollution is the least, yeah. And well, photometric quality, yeah, is excellent, yeah. Now relatively cheap, yeah, well, we are working at the international level, and all our data, yeah, are, well, freely accessible. Well, the cons are, of course, it's a non-steerable telescope, limited by 102 seconds of integration, but as I said, you may afterwards, yeah, co-add the images, yeah. And so we are having a lot of fun, yeah, with the telescope, and we invite anyone interested, yeah, to join us, yeah. Oh, now, just for the pleasure of the eyes, yeah. Well, the sky that one can see Devasthal, yeah. We see the Orion Nebula. That was in December 2022, yeah. And well, we have the impression here that the stars are rotating from right to left, yeah. So easy now to pick up, yeah, where the North Star is located. This is the same time-lapse bed where we are integrated, yeah, the light along the trajectories, yeah. Now, if you see the same sky in the spring, yeah, okay, it starts here. Oh, now you see the Orion Nebula, but turning in the other direction, yeah. So is it possible that we see stars moving in one direction and the other time in the next direction? Question, no? Okay. What will be nice here is that we will see the Milky Way with Scorpion constellation, with Jupiter also in that constellation. So now you see here, you may guess, this is the galactic center, and here is a Scorpio nebula, yeah, Antares, and Jupiter is over here, yeah. So that's all. Well, some images, yeah, of the sunsets, yeah. You know that the Beatles, yeah, were in India, and they composed a very nice song, yeah. But the fool on the hill sees the sun going down, and the eyes in his head sees the world spinning around. So very nice. Okay, now if there is any question, yeah. Yeah.
And questions?
Yeah.
You can turn on the light.
Yeah. Oui, ça va là. Yeah.
So, questions?
Yes.
Just needed that before that about the light pollution.
Yeah.
Very first, I think. That one. Yeah.
Oh, the first one I showed
Yeah.
at the beginning is
Yeah.
this year, yeah, because
year
of the
only.
comet, yeah,
Yeah.
because of the comet, yeah, yeah. But already a few years ago, yeah, well, we would raise, you know, attention to that danger of having, you know, car lights illuminating, you know, flashlights, yeah, and now it's becoming really problematic, yeah.
Yeah.
It's something that we need to be done to remind people that, you know, an observatory, yeah, should be. Excuse me?
But we have to keep on reminding them.
Yeah, yeah.
So every time new driver comes and they don't.
Yeah.
I can see the several torches were there of the security persons and all. Which one
Yeah.
is the dangerous?
So like, like.
Yeah, exactly, exactly.
Mhm.
So that's what actually I'm suggesting. Not, yeah, that I don't know why it came up.
Here you say?
Not
Here.
here, not here in the Devasthal.
In Devasthal. Yeah, I see. Mm. Yeah. It's an important detail.
Yeah,
Yeah.
exactly. Data is public. Yeah.
Any other questions or anything?
Yeah, it was a very nice talk. And is there any plan to use, say, infrared detector
Yeah.
for later on once you complete this survey?
Yeah,
Uh,
well,
other
very good
titles?
point. Yeah, we were very much interested. We inquired already about that possibility. Yeah, at the moment there is no infrared detector working in the TDI mode. Yeah, and infrared detectors are very expensive. Yeah, yeah, but we would love that. Yeah.
So how do you know that when we have this problem? Because in the medical year,
Yeah. 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 Well, personally, I think that a very nice activity, yeah, well, especially for engineering departments, yeah, would be to see if we could replace mercury, yeah, with another liquid, reflective liquid, okay? And I'm sure there are solutions, yeah, because people already inquires about installing a liquid mirror telescope on the moon, yeah? And some people came with some ionic liquid, yeah, which could be adequate, yeah? Now, remember that Paul Polikson, yeah, constructed a 6-meter liquid mirror telescope, yeah? Much more simple, the concept, yeah, but involving more engineering, yeah, but he has already all the blueprints, yeah, to make one, yeah? And I think it would be fantastic, yeah, to think about, you know, well, 6 or 8-meter liquid mirror telescope, yeah? Well, with a new liquid, yeah? And well, maybe infrared detectors by that time, yeah, who knows, yeah. But I think it would be a very nice venture for the future, yeah. So I think here, if we could manage, yeah, well, getting, you know, the best we can from the telescope during a 5-year period, yeah, then we have a huge amount of data, and we have from this data, yeah, try to come out with the best, yeah. I think that we need the next step after, yeah, not just continue with a 4-meter mercury liquid mirror telescope. I think it would be nice, yeah.
definitely we need some scientific result, make a public noise.
Sure. Yeah.
Because they are that kind of result and noting this kind of bigger kind of, right? So here in this telescope, this 5-year is dictated by the liquid molecule, right?
No, I don't think so. Yeah.
I mean, it's like it's 5 years. So we can extend
Well, you may extend its life. There is no limitations there. Yeah.
like fiber optic, we can extend it.
Yeah.
But this telescope also. There is
Sure,
certain time, right?
exactly. Yeah.
And it works for even longer period.
But you see, there is a GWST after HST, yeah? Yeah, and therefore I say, when this case, yeah, one should just explore, you know, what are the best avenues, yeah? Well, of not having a too expensive project, but which could drive, you know, a lot of interesting scientific results, yeah? And, well, I'm not sure that it is a liquid mirror telescope, the future, yeah, maybe something else, but it would be nice to be proactive and to think about, I mean, future projects. Yeah.
The most difficult part in this aspect, what do you find? Which one is the most difficult part? Once the telescope is in operation.
Now,
So now, for example, mercury, controlling mercury, or is it?
No, I think it's well under control. Well, I mean, we could ask.
Not in this case. What most challenging part of this
Yeah.
to predict this one?
Well,
Most challenging part. I mean,
you see, well, I think the most worries we had was about mercury vapors. Yeah.
so this ionic,
Yeah.
if it is
Mhm.
developed, well established, then we
Yeah,
will
because
use-
Paul, was handling, well, mercury with a 6-meter liquid mirror telescope. Yeah. And then when, well, we came with the idea, to try to confine the mercury vapors, inside, the charcoal box, and see what was the effect. And when we were all very skeptical whether it would work, and then we were all surprised that it worked extremely well, that we had during, the first pouring of mercury in the dome, so which was already under the mylar film, and we already had, the extractor of vapors, and then we had the detector measuring the quantity of mercury vapors. We could have taken away our mass. We didn't know that, So I think the ending situation is under good control, but we would like to get rid of mercury, because, well, it's prohibited everywhere. For instance, in Europe, it's impossible to import mercury in Europe today. And I think the same will happen sometimes here,
and also the position of the waste.
Yeah, sure.
So if there are no further questions or comments, then let's thank again.
Yeah, with pleasure. Voilà.